Welcome to T3 Knickel AI. Today, we are embarking on a journey into the heart of modern civilization. Look around you. Almost everything you see, the food on your table, the materials of your home, and the vehicle in your driveway, was likely moved or created by an internal combustion engine. For over a century, this mechanical marvel has been the primary driver of human progress. But how does a simple mixture of air and fuel create enough power to move mountains? Today, we go beyond the surface. We will dismantle the physics, the chemistry, and the incredible engineering that makes these machines roar. From the first spark to the high-tech future, this is the ultimate masterclass on the internal combustion engine. To understand where we are, we must look at where we began. Before the internal combustion engine, there was steam. But steam engines were external combustion, they were massive, inefficient, and dangerous. In the late 19th century, visionaries like Nicolas Otto and Etienne Lenoir asked a radical question: what if we put the fire inside the cylinder? In 1876, Otto perfected the four-stroke cycle, a design so efficient that it remains the global standard today. Shortly after, Carl Benz put this engine on three wheels, and the world changed forever. We transitioned from animal power to mechanical power, shrinking the planet and expanding human potential. At its heart, an engine is an energy converter. It turns chemical energy into thermal energy, and then into mechanical work. This happens through the famous four-stroke cycle. Phase 1, Intake. The intake valve opens, the piston descends, and a vacuum draws in a precise mixture of air and fuel. Phase 2, Compression. Both valves close. The piston rises, squeezing the mixture into a tiny fraction of its original volume. This increases the temperature and pressure, making it ready to explode. Phase 3, Power. The spark plug fires. The resulting explosion creates a massive pressure wave that hammers the piston down. This is the only stroke that generates actual work. Phase 4, Exhaust. The exhaust valve opens, and the piston pushes the waste gases out. This cycle repeats thousands of times per minute, creating the continuous rotation we call RPM. Let's look at the components that survive this incredible stress. The engine block, often cast from aluminum or iron, it houses the cylinders. The pistons, these are the hammerheads that receive the blow of the explosion. They must be light yet incredibly strong. Connecting rods and the crankshaft, as we discussed in our previous video, these parts turn that vertical punch into rotational torque. The valve train, controlled by the camshaft, these valves act as the lungs of the engine. The cylinder head, this sits on top of the block and contains the combustion chambers, spark plugs, and fuel injectors. Every part must be machined to a tolerance of less than the width of a human hair. The perfect explosion requires the perfect ratio. For gasoline, that is the stoichiometric ratio, 14.7 parts of air to 1 part of fuel. But modern engines are smarter. With direct injection, we spray fuel at over 2000 psi directly into the cylinder. We also have turbochargers. A turbocharger uses waste exhaust gas to spin a turbine, which forces more air into the engine. This allows a small 2.0-liter engine to produce the power of a 5.0-liter engine from 20 years ago. It is efficiency through forced induction. Inside a cylinder, temperatures can flash to 2500 degrees Celsius. This is hot enough to melt the entire engine block. To survive, the engine relies on its cooling system. Water and antifreeze circulate through jackets in the block, carrying heat to the radiator. Equally vital is lubrication. Oil is the lifeblood of the engine. It creates a hydraulic wedge between moving parts, ensuring that metal never actually touches metal. If you lose oil pressure, the friction will weld the engine solid in a matter of seconds. This is why regular maintenance is not an option, it is a necessity. Not all engines need a spark. Enter the diesel engine. Invented by Rudolf Diesel, these engines rely on compression ignition. By compressing air until it reaches incredible temperatures, the fuel ignites the moment it is injected. Diesel engines are much more efficient and produce massive amounts of torque, which is why they power the world's shipping, trucking, and heavy industry. However, because they operate under much higher pressures, they must be built heavier and stronger than gasoline engines. As we look to the future, the internal combustion engine is facing its greatest challenge, electrification. But the story isn't over. We are seeing carbon-neutral synthetic fuels and ultra-efficient hybrid systems. The internal combustion engine built our modern world, and it will continue to power our most heavy-duty needs for decades to come. It is a masterpiece of human ingenuity. Thank you for joining this masterclass on T3 Knickel AI. If you want to see more deep dives into the machines that power our world, make sure to like and subscribe. Until next time, keep your gears turning.